Thank you very much, Lane, and thank you very much, Mr. Shaw. That was very interesting viewpoints from Department of Energy. And now for the next speaker, that's Mr. Paul Hines. He's Vice President of Power Systems EnergyHub. He will talk about aggregating many small energy devices to build virtual energy storage. Take it from here, Paul.
Thank you. It's a real honor to be here today, and I really appreciate the opportunity to speak with all of you. So as we cue things off today, I wanted to start by really thinking about why it is that that we're trying to do what we're trying to do here. So let me share my slides really quickly. Yeah, so I'm going to talk about virtual energy storage. So I'll explain what that means in a few minutes. But I'm going to start off by thinking about why we want to do this. And to do this, I'm going to kind of run through a little thought exercise. For about 15 years, I was a professor in electrical engineering and power systems at the University of Vermont. And this is kind of an exercise I would often give to my undergraduate students. And it actually was really insightful to think about what does it look like to really decarbonize the electricity sector? And so let's just take a relatively small state of Vermont, where I live, and think about what it means to decarbonize. And so here we've got a typical July day, and this is the load consumed. So we've got about 1,000 megawatts of peak load in the state. And, you know, people consume more during the day and less at night, but there's kind of a normal amount of electricity consumption. If we then decide that we want to electrify transportation, that's going to produce a lot of extra load. And so this is an uncontrolled charging scenario where a lot of people are charging at work. And so we've installed a lot of at-work charging stations, and a bunch of people are charging during the day. And we've dramatically increased the peak load in Vermont up to almost 1,400 megawatts. So an incredible increase in peak load. So now let's think about the supply side. So this doesn't, you know, we probably would also electrify heating, but this doesn't model that. So let's think about adding some solar. So Vermont, like many states across the US, has fairly aggressive clean energy goals. And so let's say that we want to get 40% of our energy from solar. So Vermont has some cloudy days, some sunny days, and you get a solar energy profile, something like this. And we've also got a lot of hydro, particularly from our friends up north in Canada. And let's say that we get about 20% of our energy from solar hydro, and we kind of use it to fill in some of the valleys at nighttime. Then we say we build a lot of wind. There is quite a bit of wind, particularly up in the Green Mountains here in Vermont. And let's say we added about 40% of energy wind. So now the supply, so we produce enough energy to meet the demand. Sometimes the supply is actually going off the page. And let's think about what happens when you put these together. So here on the top, you see the demand. On the bottom, you see the supply. And in the middle, you see the difference between the two. They don't line up. That's sort of obvious. Sometimes you've got too much supply. Sometimes you've got too much demand. If we just look at the difference between the two, the difference between the supply and demand, this is what flexibility looks like. And oftentimes we think about energy storage trying to solve this problem, shifting load from one time to another. But there's a lot of ways that we can actually solve this problem. But this is the challenge. We've got this variable supply. We've got to figure out how can we enable supply and demand to align in real time. We've got two main sources of flexibility. So this session today is really about energy storage. Energy storage is enormously valuable. And energy storage takes energy that would be consumed at one period of time and moves it to another period of time. So essentially, it's a device. Batteries are devices that shift energy in time. You don't only have to do that with energy storage. We can also do that with demand flexibility. Things like thermostats, electric vehicle charging, batteries in people's homes, refrigerators, all sorts of devices that get plugged into the grid have this ability to shift when it is that they actually consume energy. And that load shifting actually can produce a lot of value that looks very much like energy storage. So we're going to call, for today, we'll call these aggregations of smart energy devices that can shift load, we'll call them virtual energy storage. The really cool thing is that there's enormous growth in this space. There's enormous potential for new devices to get added and be transformed into virtual energy storage. So today in the US, there are about 17 million thermostats, about 2 million electric vehicles, and about 2.8 million rooftop solar systems. And a really rapidly growing number of those rooftop solar systems include batteries. And so as you think about what it means to decarbonize electricity in North America, that means, over time, over the next, let's say, the US goal is to decarbonize electricity by 2035. Maybe we won't get there, but let's say that we do. That means eliminating most of the fossil fuel generation by that time, rapidly increasing wind and solar capacity. And in order to balance that variable wind and solar, we're going to have to build an enormous amount of energy storage, but also, I believe, an enormous amount of flexible demand capacity. So by this particular set of modeling that I've looked at from various people, we end up with we need something like 500 gigawatts worth of flexible demand and energy storage by the time we get to 90-95% decarbonization. So that's an enormous amount of capacity. That's like 500 large nuclear power plants worth of flexible energy systems. So I work at EnergyHub. We've got our vision, our mission is to enable a carbon-free distributed energy future by integrating any customer device with the grid, providing this type of flexibility and reliability to the grid. This is a bit of an eye chart, but just to kind of give you a sense of what we do. We transform things that get connected at the grid edge, like thermostats, EVs, batteries, and all sorts of other things. And we work really closely with a wide variety of different industry players on the left-hand side to take devices that they make and consumers buy and install in their homes and transform them into these valuable grid resources. On the other side, we work with electric utilities all over across North America and work with them to figure out how can we use these aggregations of smart devices and turn them into grid resources. So the software solutions that EnergyHub, along with many other people across the country, a number of other companies in the world today provide, is called a Distributed Energy Resource Management System, or DERMS is kind of the acronym. And that thing needs to do several different things. We need to figure out how do we provide sort of form resources, enable situational awareness for electric utilities and demand aggregators, optimize the control of those resources, and provide performance measurement. And we do that with a lot of different types of devices. So let's just, before we wrap up, let's take a look at what happens when we apply this in the real world. And so this is the demand from many thousand thermostats in the southwestern United States. And so in this, on the x-axis, you see time, the y-axis, you see power. And, if we had not done anything, you wouldn't, this would kind of have a nice ordinary curvy shape. But we did a couple of things here. So we helped all of these thermostats to pre-cool. And in this particular place, this is a very sunny location. We want to absorb as much solar as possible. So energy is really cheap in those early afternoon hours because you've got a lot of solar still. But then in the early evening, demand picks up and we really want to reduce demand. So we're going to reduce demand during the peak. And then after the peak, you get a bit of recovery. And so what we've done is we've sort of like a battery, we've shifted load from period when energy is scarce to a period when energy is plentiful and enable these thermostats to act like a battery. We can also do this with electric vehicles. And so here is some results from one of our electric vehicle programs. We've got a period when energy is scarce or expensive in the early evening hours, and shown in gray. And we're going to reduce demand dramatically during that period, shifting load away from that expensive peak load period, essentially enabling this group of electric vehicle charging stations to act like a battery. And we can do this with real batteries also. So many people install batteries in their homes, particularly people who have solar. We're actively running a number of programs in which we're able to take those batteries, turn them into grid resources, and shift load so that they can charge during the day, early morning hours when there's lots of solar capacity available, and then discharge in the early evening hours when peak loads occur, producing dramatic savings for the electricity industry and a lot of value for consumers as well. What I love about these types of programs is that, in addition to utility scale storage, we're able to provide a lot of value to consumers. And so people are benefiting by participating in the energy transition. And then to think about what happens looking forward, I came to EnergyHub from a company called Packetize that helped found, and we developed some algorithms that allow us to really get beyond the idea of just calling peak load events, but actually actively shaping demand. So here's some work in which we took a wind production from a particular day and said, can we take about 300 DERs and enable them to actively shape load in real time? We're able to show that you can actually take DERs and turn them into load shaping valuable resources, just like batteries. We can actually have them shape load in real time. We've been able to show that with real devices. So here's a set of about 250 water heaters tracking with a PJM frequency regulation, so like grid balancing signal in real time. And so this is evidence that we can actually move to a world in which all of these devices are actively shaping load in real time, just like batteries. Just to kind of summarize what we need looking forward, we really see that customer-sided energy devices can help to balance the grid, just like energy storage. But looking forward, we really need to figure out how do we develop incentives for both flexible demand and energy storage so that we can build this at enormous scale, the enormous scale that's needed to decarbonize electricity. And then I think I really appreciate the international nature of this event. We really need continued international innovation to enable the technology and policies that will get flexible demand and energy storage to the massive scales that is needed. Thank you.